consider another problem. H of n is equal to 0.99 raised to n u of n plus 3. And for this problem, the impulse response is given. We have to check whether it is causal or non-causal, whether it is memoryless or no, whether it is stable or unstable. So the given signal is 0.99 raised to n u of n plus 3. As it is this way, let's draw the signal. 0.99 raised to n is the signal running from minus infinity to plus infinity. But it is multiplied by u of n plus 3. And I hope we know what is u of n plus 3 signal, which will be running from minus 3 to infinity. So when this exponential signal 0.99 raised to n is a decaying exponential. So when this gets multiplied with these values, so we'll be having such kind of a signal. So the signal will be in this way. So it is at minus 3, some value at minus 2, the signal will be having the value, at minus 1 it will be having the values. So let's say the signal runs in this fashion. So the values are this way. So they'll be running from minus 3 to infinity, and their amplitudes are decreasing as the power is increasing. So let's say positive 1, n is 1, 2, and so on. So this is a signal. Now for this signal, as we can see, let's check about the causality. So from the definition of the causal, we know that our h of n should be equal to 0 for n less than 0. Is it true or not? We need to check. Now this is our condition. H of n is equal to 0 for n less than 0. So if n less than 0 means this side, like minus 1, minus 2, minus 3, and so on. And to be just, it's clear that on the left side the signal is existing. So the system is certainly non-causal because it doesn't satisfy this condition. So it is having h of n is equal to 0, h of n not equal to 0 for this. It is not equal to 0 for n less than 0. Like minus 1, it is having the value, whatever it may be, it's having the values on the minus side. If at least one of them is existing, then at minus 1 also, if the value was present, it could have been a non-causal system. So it is non-causal. So the conclusion is the system is non-causal. Then let's check about the next property. The system is non-causal. So let's check about the next point, memorylessness. So memoryless, we'll check with this condition, h of n is equal to 0 for n not equal to 0. Means the signal should be existing only at the 0th instance, and it should be 0 for other instances on the left or even on the right. Now clearly the signal is existing on either side, on the left side also, or on the even on the right side. So the signal is not just present at the 0th instance, it is present for both the sides, left as well as right. So the conclusion is the system is having the memory, or it is not memoryless. So it is not memoryless. It is not memoryless. Then the next point is regarding the checking of stability. So stable, the system is said to be stable if this condition is satisfied. Let's check this condition wherein summation k from minus infinity to plus infinity, the magnitude of h of k is less than infinity or no. So for checking this one, let's write the summation for this signal. Now as we do indexing the same signal, we can refer it as h of k, and in place of this n, it would be referred as k. In place of n, I can refer this axis as k for solving the stability. Then k runs from the lower limit, like k runs from minus infinity to plus infinity in general, but for this problem, k's value is from minus 3 to plus infinity. So k runs from minus 3 to plus infinity, 0.99 raised to k. And for this summation, we can't apply any of the equation. So it is not in the standard form to apply the equation. So for that, we need to have the lower limit as 0. And to make this one as a 0, let's consider another variable in place of k. So this m is equal to make this 0, what should be the condition? Let's assume that. So let m is equal to, what should be the condition to make this lower limit as a 0? Let m is equal to k, let m is equal to k plus 3. If m is equal to k plus 3, then when I substitute k as minus 3, then my m goes 0. So by taking this consideration, we are taking up this limit. So this summation will become as, now when we take this, so our summation would be, now it is with respect to m, and this m is equal to, when k is equal to minus 3, our m becomes 0. Our m runs from 0 to, now when the value of k is infinity, m tends to infinity. So let's write it. Then 0.99 raised to 0.99 raised to this k. The value of k is given by n minus 3. So let's write this one as n minus 3. Now let's solve this. Now for this equation, now 0.99 raised to minus 3 is a constant. So we can write this 0.99 raised to minus 3 outside of the summation. So this 0.99 raised to minus 3, let's take it outside. Then this summation can be written as summation m from 0 to m from 0 to infinity. It is 0.99 raised to 0.99 raised to this m. That's it. And we know that it is in the standard form. So summation, as we used the equation, if summation m raised to or n raised to n to summation k or any variable that is running from 0 to infinity, and this value is less than 1 and that power is raised, then certainly, as we know, the summation k is equal to 0, summation k is equal to 0 to infinity alpha raised to k is given by, as we have applied, this will be given by 1 minus alpha, as long as this alpha is less than 1, as the value of this alpha should be less than 1. If the value of alpha is less than 1, we can use this. Now clearly it is less than 1, so we can write the solution of this one as 0.99 raised to minus 3, and this value is 1 by 1 minus point, let's write it as 1 by 1 minus 0.99 raised to 0.99, that's it. And this works out to be 103, around 103 it works out to be. So let's write, so it works out to be 103.6, it is around 103.06. so certainly it is less than infinity, so our system becomes stable. The system is stable. So this is regarding the solution of this discrete. So we can see some other discrete problems if there is a problem in solving them. Then let's go for solving a continuous time signal. A continuous time, the similar kind of problem. So let's consider this problem. Here, the impulse response of the system h of t is given as e raised to 2t u of e raised to 2t u of t minus 1. And we need to check whether it is causal or not, whether it is memoryless or not, whether it is stable or not. So just we can see, we can draw the signal. The h of t signal is this one, and e raised to 2t is actually a increasing exponential, but as it is getting multiplied with u of t minus 1 signal, so when these two are multiplied, we get only this portion of r e raised to 2t. So the signal runs from 1 to infinity. Now, regarding the causality of the system is not there on the left hand side of the axis. So it is there lying only on the right hand side. So it is causal. So as it satisfies the condition h of t or h of tau, we can write h of t is equal to 0 for t less than 0. Because for t less than 0, this is the thing that is t less than 0. So for t less than 0, the signal is 0. So the conclusion is h of t is 0 for t less than 0. The system is said to be causal in nature. So it is causal. Then the next thing is whether it is memoryless or no. Yes, the condition for memoryless is h of t should be equal to 0 for t other than 0. h of t should be equal to 0 for t not equal to 0. But for t not equal to 0 means 1, 2, 3 and so on it could be, and even on the left side. But on the right hand side, when t is 1, 2 and so on, the values of the signal exist. Hence, our h of t is not equal to 0 for t not equal to 0. So, the system is not memoryless. The system is not memoryless. Then, the next point is regarding the system is not memoryless. It is with memory. And the next thing is regarding the checking of stability. The system is said to be stable if the integration, as it is a continuous signal, we need to take up the integration from minus infinity to plus infinity, h of tau d tau. If it works out to be less than infinity, then the system is said to be stable. Otherwise, it is unstable. So, for solving this one, now let's take up the limits. The signal is running from 1 to infinity. So, the integration 1 to infinity, h of tau is nothing but e raised to 2 tau. And u of t minus tau is being taken care by this equation itself, this limits itself. So, when we go for integration of this, the integration of e raised to 2t is nothing but e raised to 2t itself. So, divided by 2 and 1 to infinity. The limits when we substitute. So, the upper limit when we substitute, it is e raised to 2 into infinity is nothing but again infinity minus e raised to 2 into 1 divided by 2. And as e raised to infinity term is there here, this e raised to infinity term will make this one as anything. Infinity minus e raised to 2 is again infinity. So this is equal to infinity, and we can conclude that the system is not stable. It is unstable. So the system is not at all stable. It is an unstable system. In place of this, if it could have been like e raised to minus 2t, if the thing was like e raised to minus 2, then we could have got the thing as this integration could have been given as the value if the another problem is like e raised to minus 2t into u of t. If the problem given to us was this one, then or u raised to t minus 1, then the thing could be like, again this becomes a causal one because it is existing only on the right hand side. Again it becomes not memoryless because it is existing for the right side. From 1 to infinity it would be existing only the value instead of a increasing exponential. It becomes the signal would be in this way. So from 1 to it decreases, the signal decreases from 1 to it would be a decreasing signal up till infinity. So from 1 to it goes in this way. The signal would be running in this fashion. So it would be a decaying exponential as infinity. Up till infinity it would be decreasing. Then when we go for checking the stability of that one, then we could have substituted this as e raised to minus 2 in place of e raised to plus 2. And when we substitute it as e raised to minus 2 tau, the integration of this one we get as we obtain it as e raised to minus 2 tau divided by 2 minus 2. So the limits would be from 1 to infinity because the range of the signal we have not changed. And when we solve this one, this could have been resulted as e raised to, when we substitute it is e raised to minus infinity minus e raised to minus 2 divided by minus 2 divided by minus 2. When we get this, and we know that this equation e raised to minus 2, this e raised to minus infinity is equal to 0. As we know that e raised to minus infinity is equal to 0, so we can write this e raised to, this value becomes e raised to minus 2 divided by 2. And certainly which will be less than infinity, and in that case the system would be stable. So if what I mean to say is, if the exponential is increasing, the system becomes unstable, and if the exponential is decreasing, the system becomes stable. Okay, so these will be the problems. So the next problem regarding the magnitudal value, I will see that one in tomorrow's class. So we'll stop it here.